Hi all of you. Let's start with the chapter called Nitric Acid, HNO3. This is one of our volatile acids and we call nitric acid as aqua fortis. Aqua, water. Fortis, strong. We call it as strong water. In order to prepare nitric acid, right, we have a few simple reactions. How does it start? It is all from this one. So I start with the chapter called Nitric Acid and the formula is HNO3. Keeping it very simple. Water vapor reacts with oxygen and NO2, nitrogen dioxide. However, it's a reversible reaction forming nitric acid. This is a simple method of preparation of nitric acid. I am not balancing it right now, please. This reaction, when I will be writing in one of these answers, I shall be balancing it then. So as of now, remember, to produce nitric acid, this is one of the methods. A general, basic, simple method. We also have a laboratory method of preparation of nitric acid. Okay, and we have industrial method. So let's start with our first answer, lab method of preparation of nitric acid. The salt which I'm going to use for preparation, I call it as either a Chile saltpeter or I call it as a Bengal saltpeter. I have two salts in which I can prepare nitric acid. Chile saltpeter, I call it as NaNO3 and Bengal saltpeter is KNO3. Yeah, KNO3. So we have NaNO3 and KNO3, right, with this. So these are the compounds. Lab method, if you observe the diagram, it looks something like this. Unlike a lid which is made up of glass. A retort stand, okay, a mesh wire, a flame. In this, we have a liquid and that is an acid which is again conc H2SO4, which is a reactant. And we have either of these salts. Either we have NaNO3 or we have KNO3. So let's talk about the pieces of salts. Fine, perfect. The gas which evolves is HNO3 vapors in gaseous form. It is passed through a pipe, okay, and it is collected in a flask. And we have a running water. We have a tap, cold water. Okay, this is how it is. So this is the collection of HNO3 in aqueous form. And the HNO3 which I get out here, the percent purity is 50% pure. So that I'll talk about it in some time. So let's see what happens. First, if I'm talking about the reactants, we have two reactants. We have, let's take this one, NaNO3. So the reaction is as follows, students. Sodium nitrate reacts with conca sulfuric acid to form, it's going to be less than 200 degrees Celsius, similar to hydrochloric acid. It forms an acid salt which is NaHSO4. So we have NaHSO4 plus HNO3 vapors. Right. Now, if I happen to balance this, 2 hydrogen, perfect, sodium, alright, nitrogen, perfect, oxygen, 3 and 4. It's a balanced equation. No need to worry. I'll just talk in terms of first one. I'm not taking KNO3, please. You can manage it by yourself. So this is the reaction which takes place when it is below 200 degrees Celsius. If the reaction carried out is above 200 degrees Celsius, guys, problems. The same problem which we faced while making HCl. That's greater than 200. Yep. It gives me a salt which is a normal salt. This was an acid salt because of the presence of hydrogen in the salt. But now we get Na2SO4. This is a salt, sodium sulfate plus HNO3. Obviously again in gaseous form, vapors. To balance it, 2 sodium, yep, 2 nitrogen, and I think that's balanced for you all. Yep, perfect. Now, can I say this salt is a normal salt and this salt is acidic in nature, acid salt. Now, what is the problem greater than 200 degrees Celsius? We have done this. Come on, we have done it. It's a repetition. If the temperature above 200 is used, this is a lab method of preparation. This is not. Because, first problem, fuel is wasted. Second, Na2SO4, that one, this one, it forms a hard crust which is difficult to remove on the glass. And third, can I say a higher temperature may crack the glass. It may crack the apparatus. So guys, there are 3 problems out here. So a temperature used is below 200 degrees Celsius. Second, why is conch sulfuric acid preferred as a reactant? Because first, it has a high boiling point. We have done this. It's a repetition. The same answers were there for HCl for you all, right? It's a repeated thing. So I can start with my next pointer. H2SO4 is preferred as a reactant because first, it has a high boiling point. Second, it's a non-volatile. It's a non-volatile acid. It does not vaporize out smoothly. And third, it displaces a volatile acid from the salt solution. That means in this reaction, can I say this is a volatile acid? Conch sulfuric acid displaced a volatile acid from the salt, displaced the volatile acid from the salt. So it is capable of doing that. My third pointer for y'all, why is this bloody apparatus made up of glass? Wherever I see it is glass, glass, glass. Yep. What about a rubber cork? What about some metal inclusions? Nothing. Why glass? Because HNO3 vapors, these vapors are highly corrosive. And if they are corrosive, they may corrode, they may attack the rubber, and that will be a problem. So I can say HNO3 vapors are highly corrosive. That's why, therefore, entire apparatus is made up of what, guys? Come on, it's made up of glass. It does not affect glass, please. Right, perfect. It's going beautiful and smooth. So we have spoken about so many things. Why? Okay, this collection of HNO3 out here. Okay, the collection of HNO3 out here. How much pure is it? How much pure is it? Can I say the HNO3 which I obtain? Can start from here. The HNO3 which I obtain, it is only 50% pure. Yeah, that's so boring. How horrible. Just 50% pure. And the color, it has a yellow-brown tinge color. It has a yellow-brown tinge color. That is the color of HNO3 which I obtain from that. Okay, apart from that, anything else I can think of? Which acid is not used? Can I say H2SO4 is used? HCl should not be used, because if hydrochloric acid is used, I will get two vapors and both of them are volatile. HCl as well as HNO3, both are volatile. So I should not use HCl as a reactant out here. I don't think I remember much about it more, but these are the pointers for the laboratory method of preparation of nitric acid, right? So I spoke about the purity, the yellowish brown tinge. We spoke about the reactants. We spoke about the product form, the temperature used. Why is this reactant used? And why is this apparatus made up of glass? Now, where does this yellow tinge come from? The yellowish brown color. HNO3, check what happens. This is my second answer. Where does it get the color from? This HNO3 na, it's a bad substance. It's like a house in which the family members keep on fighting. They keep on fighting. Like HNO3 internally keeps on bloody fighting. And it fights, and there is an internal breakup. It automatically, I have done nothing. I have neither heated nor given an electric spark or supplied some light energy. Nothing. HNO3, I've kept in a bottle just like that on a table. On its own, internally, there are so much of fights. There is a decomposition. HNO3 decomposes to give water plus nitrogen dioxide plus ideally nascent oxygen. Now, this nitrogen dioxide is reddish brown in color. Now, that's where the problem lies. Nitrogen dioxide is reddish brown. This is the cause. This is the part. This is the substance which imparts the color to nitric acid. Right? So the nitric acid yellow-brown tinge comes from this bloody substance, nitrogen dioxide. And because this decomposes into these three substances, nitrogen dioxide is the one who is the root cause of giving a color to the nitric acid. Yep. Okay. This yellow color, this impure nitric acid, the yellow color can be removed. Okay, how can it be removed? First, by bubbling air or carbon dioxide. Now, what I'm doing is, look, 100% of nitric acid won't decompose. Nope. It is some portion. Let's say 30% of nitric acid decomposes to give this plus this plus this. 100% won't take possible. It's not going to be possible, full decomposition, right? So when you bubble air into this solution or bubble carbon dioxide, that air will oxidize. Oxidize means give oxygen. Oxidize nitrogen dioxide and say, oh, nitrogen dioxide, chalo yaar, come on, just patch up, man. Patch up with oxygen and recombine to form nitric acid. So can I say that patching up takes place, right? That involvement of the third party. Come on, do you know when there is a fight between a family or within the members of the family, doesn't a relative come like a stupid person in between, interfere in the matters and try to get back the family together? Yep, we hate them, right? But let's not get into that. But I can say it's always that the third party comes and who makes the things, in a bit more proper manner, it furnishes the things. So that is what happens. That bubbling of air or carbon dioxide says to nitrogen dioxide, oh, nitrogen dioxide, come on, oxidize, combine with oxygen, get together, form nitric acid. That's what happens. So bubbling of air or carbon dioxide, it oxidizes nitrogen dioxide to nitric acid. And the second way of removing this yellow tinge, what are we trying to do? We're trying to remove that yellow tinge. Okay, this is the removal of yellow tinge. And the second method of removing is bubbling air of carbon dioxide, passing water, dilution with water. So these are the two techniques in which the yellow-brown tinge of nitric acid can be removed. So till now guys, I've done 3 answers. My first answer is about the lab method of preparation. The second is about this purity, the color, and where does the color come from. And the third is how to remove this color, how to remove the yellow-brown tinge. First, bubbling of air or carbon dioxide. Second, dilution with water. Go through these 3 answers. We'll go with further, a lot more to happen. The fourth answer, industrial method of preparation, which we call it as the Oswald's process. The industrial method. Now, the Oswald's process consists of 3 chambers. So let's study our way. The first chamber, in which there are 2 inputs. Then comes the second chamber, and finally the third chamber. Alright, a very stupid diagram, but you will understand beautifully. Okay, the inputs, the 2 reactants which I'm gonna put in this is dry ammonia gas, of course, and air. To be more precise, oxygen actually, right? So air, dry oxygen, and dry ammonia gas. So the reaction takes place in the first chamber, and the name of the first chamber is a catalytic chamber. The second chamber, the name of this chamber is oxidation chamber, and the third chamber is called absorption tower. Fine. So when I give 2 inputs into the first chamber, students, the reaction takes place as follows. Dry ammonia gas reacts with oxygen. Oh shit, that's O2. It's O2, not O5, of course. Yeah, please. Yep, that's O2 for you. Reacts with oxygen in the presence of catalyst platinum around 700 to 800 degrees Celsius. It forms NO, nitric oxide, plus water, plus tremendous amount of heat energy. Approximately 21.5 kilocalories of heat energy is produced. Tremendous. So it is a highly exothermic reaction. Fine. If you happen to balance this, okay, we have 2 oxygen. We have 3 hydrogen, which is an odd number. I don't like odds. Here are 2. So even if I put a 2 out here, 2. Problem is, it's going to be 2 nitrogen. So if I make a 2 nitrogen, this is going to be 2 oxygen and 3 oxygen. Oxygen becomes odd. So I double the process, make it 4. So if I make a 4 nitrogen, this is going to be a 4 nitrogen out here. Perfect. Nice. 12 hydrogen. 12. To make a 12 hydrogen, there's going to be 6 out here, and 4 plus 6, there will be 5 oxygen out here. So this is going to be the reaction. 4 ammonia plus 5 oxygen gives 4 nitric oxide plus 6 water molecules and a highly exothermic reaction. Fine. What happens is, in this first chamber, NO is formed and moisture. The NO gas goes ahead in the next chamber. Alright, let's start. We have NO and this is an oxidation chamber. That means I am supplying a lot of oxygen from the top. Actually air which has a lot of oxygen. So in the second chamber, we have nitric oxide plus a lot of oxygen. It gives me nitrogen dioxide and approximately 50 to 60 degrees Celsius. That's it. Now, a question. The temperature is reduced drastically. Second thing, only initially in this chamber, the reactants are heated. Only initially. That means for some time, I will be heating these reactants and then I will stop the heating. Why will I stop the heating? Because it is a highly exothermic reaction. Can I say this heat is sufficient to continue the reaction in the forward direction? That means with the help of the amount of heat produced, the reaction can, go on and on and on in the forward direction. So I can say this is a question. Why is heating done only initially, right? Second, a very less temperature is used in the second reaction, forming nitrogen dioxide. Reddish brown fumes, guys. Alright. So from the further part, there are two gases going further. One of them is nitrogen dioxide plus oxygen because a lot of oxygen is supplied. So guys, please remember the ratio of oxygen in this experiment has to be very high. You need to supply a lot of oxygen from all the chambers, from here also, everywhere, because a lot of oxygen is involved, in the reaction, right? So remember, a lot of oxygen is utilized. And finally, in the absorption tower, we have quartz layers on the top. So these are quartz layers. Now what's that? Why? And just like when you go to any theme park, when you stand in a queue, the water sprinkles from the top. Yeah, like a soothing sensation. Similarly, from the top, there is a water sprinkling out from the top. So this is H2O. Now, why the hell is this? Check. And why the hell is this quartz? Check this. The two gases which have entered into the third chamber. Which two gases? I'm talking about nitrogen dioxide and oxygen. Please remember. These two gases, if there is no quartz layer or there is no obstacle, no hindrance, the gases will go up very fast. The gases are light, they are rare. Yep. They will go up very fast and the combination won't be proper. Whose combination? What I'm trying to do is check. Check the third one. NO2 plus O2. It reacts with water forming HNO3. Now if I balance this, that's balanced for you. Okay, you can check it. Now what I want to do is, I want to combine this and this. So if these two gases go up very quickly, the combination of all three of them will not be that smooth. So what I'm trying to do is, there are pores through which the gases are definitely going to go up, but slowly. So can I say quartz? Quartz has three advantages. First, why is quartz used? Quartz is acid resistant. Do you remember HNO3 is corrosive in nature? Quartz is unaffected by HNO3. Second, quartz slows down the motion. It slows down the movement of the gases. And third, it helps, okay, because of the slowing down of the motion of the gases, the quartz layer helps in good combination, okay. It helps in good combination of the gases forming nitric acid. So these are the three uses of quartz, guys. Remember the three uses of quartz. And finally, what I get, what I achieve is HNO3 in the aqueous form, and that can be collected from the bottom. This is how my industrial method works. So it was a very simple process. If you use temperature higher than this, then there is a possibility of, NO which is formed will not be formed in that smooth manner. And if you use temperature below 700, the combination will not be that great. Okay. So this was about my entire process. Why am I using quartz? Why a lot of oxygen is used? What are the reactions? Fine. So this was about HNO3. Now, HNO3 which I obtained from that method, from this method obviously, okay, that's my fifth answer for y'all. This HNO3 is again only 50% pure. I'm not liking this at all. And again the color is yellow brown tinge. Now what I'm thinking is I want pure HNO3. What I'll do is I will heat HNO3, I will heat it, okay, heat it till the boiling point. So as I heat HNO3 till the boiling point, that is approximately 121 degrees Celsius, I get approx 68% pure, and that color is again yellow, but a lighter shade of yellow. So come on guys, the HNO3 which I obtained from this method or lab method is only 50% pure and the color is yellow brown tinge. If I want to purify it, I'm going to heat it. I heat it up till what temperature? This, to get 68% pure, but again the purity is not up to my expectation. What if I heat it more than 121 degrees Celsius? If I do that, then you will get the vapors of HNO3. You won't get HNO3 liquid, you will get the vapors of HNO3. Okay, and those vapors again, you have equal proportion of water and vapors of HNO3. So you won't get HNO3 aqueous, it's going to be a flop show. So what you do is, you release the pressure. Check. To get more pure, this is called a constant boiling mixture. Okay, so CBM is attained at 121 degrees Celsius. So at 121 degrees Celsius, I get a constant boiling mixture in which I can say that yes guys, yes, you can't heat more than this because else vapors will start coming out. So CBM is attained at 121. To get a more purity, reduce the pressure, and introduce concentrated H2SO4. And when you do that, you get fuming nitric acid. Oh shit, man. We get 98% pure HNO3, and the name given to this is fuming nitric acid. And this fuming nitric acid is colorless. So remember, the purity can be obtained highest in nitric acid is only 98% pure, right? It's called fuming nitric acid and it is colorless. Alright, my sixth answer for y'all. Which color should I use? Blue? Yep, long time. Okay, in the sixth answer, students, what happens when nitric acid falls on the skin? That's my next answer. HNO3 on skin. Okay. When nitric acid falls on the skin, it's dangerous. It causes blisters. It forms yellow marks, yellow spots on the skin because it forms a protein. I would rather say it mixes with the skin, forming xanthoprotic acid. And the spots are almost like permanent. Okay, they leave an impression on the skin. Doesn't look good. So I can say first, nitric acid, when falls on the skin, it is corrosive. I think corrosive spelling is right. Yeah, I guess so. Okay, fine. It is corrosive. Second, it causes painful blisters on the skin. And can I say those painful blisters, okay, those painful blisters, when they fall on the skin, okay, it's harming, yeah, it itches, yeah. Painful blisters, pain, itching. And after it itches, it leaves yellow spots, impressions on the skin, forming xanthoprotic acid. And that's what nitric acid does to the skin. Alright guys, so what if we were just having a quick review. We started with nitric acid, the reactants, the Chile saltpeter, the Bengal saltpeter. Nitric acid is also called as aqua fortis, strong water. Second answer was about the lab method of preparation. The third answer, what was the third answer? It was about the color, the decomposition of nitric acid to form nitrogen dioxide, water vapor and nascent oxygen. Okay, instead of nascent oxygen, you can also have a molecular oxygen, O2. It's okay. Then we had the industrial method. Then how much purity can nitric acid be taken to? And the constant boiling mixture. And when it falls on the skin, what happens? Go through them. We'll attack few more answers. Alright. Talking about the action on indicators. We've done this. Come on. When you're talking about an acid, forget about HCl or nitric acid or sulfuric acid. Let me talk about any of the acid, right? Can I say it turns a litmus paper from its acid blue to red? It turns methyl orange from orange to pink. Yep. And it turns, the next one, it turns phenolphthalein. I'm just writing the shortcut, okay, right? In HCl, I've written the long form, the entire word of phenolphthalein. Phenolphthalein originally is colorless. It remains colorless in an acid. And then we are talking about phenolphthalein alkaline. It turns pink to colorless. Originally, phenolphthalein alkaline is pink. It turns to colorless. After this, my eighth answer is about the reaction with dilute acids. The reaction with dilute acids. Few reactions I'll take. That is the reaction with dilute nitric acid. Let's take first reaction of NaOH, which is an alkali. Then we'll take CaOH twice, which is a base. Then let's take CuCO3, FeCO3. Let's take these four reactions and react them with dilute HNO3. Now you need to write dilute everywhere, please, because in board exam, it's very crucial to mention whether the acid is dilute acid or concentrated acid, else a mark goes. You need to be very specific with mentioning about the concentration of an acid. Alright, NaOH, which is acid plus base, gives salt and water, the neutralization reaction. So acid plus base gives salt. It will give you NaNO3, NaNO3 plus water. Okay, again, acid plus a base gives salt and water. Calcium nitrate plus water. So these two reactions I have written are neutralization. Copper carbonate plus HNO3, it gives copper nitrate plus water plus nitrogen dioxide gas. And again, same, FeNO3 twice, iron nitrate plus water plus, it's carbon dioxide, right? Why did I write nitrogen dioxide? It should be carbon dioxide gas. Oh, come on, it's carbon dioxide. I spoke carbon dioxide. Alright, fine, you can write carbon dioxide. And that's okay, come on. Like, we are humans, we tend to make mistakes. But we realize, we rectify, so it's okay, fine. So these are the few reactions with acids. From here, I remember, I go back to the time, go back to the memory. In the past, didn't we study the typical acid property? It was dilute acid plus metal gives salt plus hydrogen. Then we had dilute acid plus base or an alkali gives salt and water, neutralization. Then we had a carbonate or a bicarbonate plus dilute acid gives salt plus carbon dioxide plus water. Sulfite or bisulfite plus dilute acid gives salt plus water plus sulfur dioxide. And dilute acid plus a sulfide, De, gives salt and H2S. You remember those 5 reactions, the standard forms? We have done it in acid basis salt. We have also done it in hydrochloric acid, the HCl chapter. So I'm not writing that once again. Right. So we studied about the dilute acid as reactions. We studied about the litmus, the action on indicators. My next answer is about HNO3. HNO3 is a highly oxidizing agent. So let's study about that, guys. HNO3 behaves as a highly oxidizing agent. Now what happens is, it's a partial equation method. Look, I take a test tube. Guys, this is a test tube. In this test tube, we have HNO3. HNO3 na, it's terror. It decomposes to give H2O plus NO2 plus nascent oxygen, as I said. Now, if you balance this equation, if you make a 2 out here, there will be 2 out here, and there will be 2 out here. Is that okay? I guess nope. 4, no, it's not okay. This is nascent. It has to be 2 out here. So in this pretext, 2 nitrogen, fine. The oxygen are 2 plus 4 plus 2. 2 plus 2 plus 4 is 8. 8. And there is 6 out here. 4 hydrogen. Let's make a 4. So this is 4. So 4 hydrogen, 4 hydrogen. 4 nitrogen, 4 nitrogen. Alright. And 12 oxygen. 2 plus 8 plus 2. 2 plus 8 plus 2 is 12. You can divide each term by 2. So eventually it becomes 2HNO3. Reversible reaction gives H2O plus 2NO2 plus nascent oxygen. So this is balanced. Now, as I said, I had a test tube in which HNO3 decomposed to give these three things. In this test tube, I add copper. So Cu will react with nascent oxygen to form copper oxide. To the copper oxide which is formed, I add more of nitric acid. Excess of nitric acid, forming copper nitrate and water. Let's balance it. Is it balanced? N is 2, N is 1. So you make a 2 out here. I think that's balanced for you. Yes, it's balanced. Now what the rule is, all these three equations which I have written out here, okay, you add them. Now when you add them, the equations on the same side of the arrow are added, and the equations on the opposite sides of the arrow can be cancelled. So nascent oxygen can be cancelled, copper oxide can be cancelled. So equations on this side of the arrow and the other side can be cancelled, but on the same side need to be added. So now if you add them, I get 2 plus 2, 4 nitric acid, copper. It gives me CuNO3 twice plus 2 water plus 2 nitrogen dioxide. And that's my reaction, which shows that HNO3 is a highly oxidizing agent because it provides nascent oxygen. Alright, now talking about few reactions with concentrated nitric acid. So my 10th answer is all about the reactions now. The first part, reactions with non-metals. So with non-metals, I can say carbon, phosphorus and sulfur. These all react with hot conc nitric acid. Again, hot conc HNO3, hot conc HNO3. It forms carbon dioxide plus water plus nitrogen dioxide. Now if you balance this, guys, nitrogen 1, 1, carbon 1, 1, oxygen 2 plus 1 plus 2. Not balanced. Even hydrogen. So can I say I can make a 2 out here? Hydrogen 2, hydrogen 2. Nitrogen becomes 2. Nitrogen becomes 2. In this pretext, oxygen is 1 plus 2, 3 plus 4, 7. We have 6 out here. Shit. What we do is try to make oxygen even. So make this 2 to make it even. Hydrogen becomes 4. So 4 out here. 4 nitrogen. 4 out here. And finally, let's check. 2 plus 2 plus 8. That's balanced for you. Right? Similarly, sulfur plus nitric acid gives me sulfuric acid plus SO2 plus, NO2, that's nitrogen dioxide, plus water. Similarly, phosphorus plus nitric acid gives phosphoric acid, H3PO4 plus NO2 plus water. Now, if you again happen to balance them, yep, there are 3 hydrogens, so you may make a 3 out here. Nitrogen can be made 3, yep. Hydrogen is 5 actually, 2 plus 3, 5, yeah. So if you make a 5 out here, 5. Oxygen will be 15. So let's make a 5 out here. So there will be 5 nitrogen. So till now nitrogen and hydrogen are balanced. phosphorus is balanced and oxygen is 15. 4 plus 10 plus 1, 15, balanced. And out here, 1 sulfur, 1 nitrogen, 4 hydrogen, 4 nitrogen as well, 12 oxygen, and oxygen is going to be odd number, so you can double the process. Hydrogen becomes 4 and 2, 6. Change it to 6. 6 nitrogen, change this to 6. Right? Left out is oxygen, 18, and out here 2 plus 12 plus 4. 12 plus 2, 14 plus 4, 18. That's it. So these are the reactions with non-metals. If I'm talking about the reactions with metals, right? We talk about two metals. Let's talk about copper and iron. Okay, this reacts with dilute HNO3 and the same reactions with conc HNO3. Four reactions. All right. Copper plus dilute nitric acid gives you copper nitrate plus, okay, what else does it give? Come on. Copper nitrate plus water plus NO, nitric oxide. Fe plus HNO3 gives iron nitrate, FeNO3 twice plus water plus nitric oxide. But if reacted with conc HNO3, it gives the same thing, copper nitrate, CuNO3 twice plus water. It doesn't give nitric oxide, it gives nitrogen dioxide. And this forms FeNO3 thrice plus water plus nitrogen dioxide. That means, can I claim that with dilute version, it gives me a nitric oxide, and with a concentrated version, it gives me a nitrogen dioxide. Also, with an Fe, it is a 2 plus salt, and with a Fe out here in concentrated, we get a 3 plus salt. So these are the few important points we need to remember. So these are the reactions with non-metals and the reaction with active metals. Talking about the reaction with magnesium and manganese. They react with very dilute HNO3, very dilute HNO3. Okay, and they form magnesium nitrate and hydrogen gas. This forms manganese nitrate plus hydrogen gas. Now guys, I have not balanced these reactions. I am leaving the balancing part for you all. It's easy. Come on, you can do that much at least. Okay, out here there is no water formed. Now, why no water is formed? The reason is this is very dilute nitric acid, very dilute. That means almost 1% acid, 1% solute, 99% solvent, 99% water. Because of the dilution, the oxidizing effect of nitric acid is so weak that a nascent oxygen is not formed. If the nascent oxygen is not formed, there is no chance of nascent oxygen combining with hydrogen, because now hydrogen usually combines with nascent oxygen to form water. But this being so dilute that HNO3 does not decompose that easily to give nascent oxygen. So HNO3 will remain HNO3, and I can say that no breakup, no nascent oxygen, hydrogen will remain hydrogen. It will not be converted into water. So with a very dilute, with Mg and Mn, hydrogen is formed, and the rest we have water and nitric oxide or water and nitrogen dioxide. Okay. So go through these reactions, and then we'll jump with the little part left for this chapter. The 11th question. Fuming nitric acid turns Al, aluminium and Fe passive. So the 11th question is about passivity. Passive is not active, passive. I will say fuming nitric acid renders means makes Al and Fe passive. How does it make it passive? Check. What happens is Al or Fe forms a oxide coating when reacted with fuming nitric acid, and because of that oxide coating, can I say that Al and Fe is like in a preserved form. Preserved form, that means it does not act with the atmosphere. It does not act with the moisture in the atmosphere. And when I want to use it, I will just remove the oxide layer and it will become chemically active. So can I say that if I want to preserve, save the aluminium and iron from being corroded or rusted, what I'll do is I'll react it with fuming nitric acid. It forms an oxide layer above it and it turns passive. Passive means it does not get affected by the atmospheric layers. And then when I want to use it for my experimental purpose, I am going to remove that oxide layer, right? So that is called passivity, right? One more thing I just forgot to tell you. In the 10th, the reactions which I had written, I had not balanced. Come on, you know how to balance it. I have taught you in 9th standard and in 10th also, most of the chapters we have balanced it. Now the time has come to evolve. Balancing, I leave it on you, right? Talking about the 12th answer, after passivity, we have few more reactions. Okay, few more reactions. The first one, this is with dilute nitric acid, dilute one. All right, we have H2S plus dilute HNO3. It gives me as a product S plus H2O plus NO2. I'm sorry, NO, because it's dilute. With the dilute, you get nitric oxide. Balancing, I'll do it in a while. Sulfur dioxide plus water, which is basically sulfurous acid, reacts with HNO3, dilute, guys, forming sulfuric acid. That's going to be H2SO4 plus NO plus, that's it, H2SO, because this itself is H2SO3 plus nitric acid, dilute, gives sulfuric acid and nitric oxide. The third reaction, we've spoken about H2S, sulfur dioxide. Which is the next reaction? It is sawdust. C6H10O5 to the base N reacts with dilute HNO3. Yep, it forms CO2 H2O NO2. Okay, the fourth one, I'm yet to balance these reactions. Okay, FeSO4 plus dilute H2SO4 plus dilute HNO3 gives Fe2SO4 thrice plus H2O plus NO. Now if I happen to balance these reactions, sulfur 1, 1, okay. 3 hydrogen, 2 hydrogen. Now this is an odd number. Ideally this should be made 2. Again, odd number of oxygens out here. 3, 1 and 1. No. So first what I'm trying to do is, I'm trying to make 2 out here. So 2 plus 2, 4 hydrogen, 2 out here. Oxygen 6, oxygen 2 out here, nitrogen 2 for the moment. So oxygen becomes 4 and oxygen is 6, not balanced. Hydrogen becomes 4, sulfur 1. We just need to balance the oxygen part. Alright. If I make a 4 out here, hydrogen becomes 8, hydrogen is 2, I want 8 total. To make 8, this can be 3. So you get 6 and 2, 8 hydrogen, 2 nitrogen, 2 nitrogen, 3 sulfur, 6 oxygen, 2 plus 4, that's it. So my final balance will be 3, 2, 4 and 2. That's balanced for you. Talking about this compound, we have 3 hydrogen on the LHS, 2 on the RHS. If I make a 2 out here, 4 hydrogen, balanced till now, 4 hydrogen. Sulfur 2, fine. Nitrogen 2, okay. Oxygen becomes 8 and 2, 10. 6 and 4 and 1, it's 11. It's not balanced. You make a 2 out here. You get 4 plus 2, 6 hydrogen. If you make a 3 out here, it's gonna be 6 hydrogen. 3 sulfur. Oxygen becomes 6 plus 2, 8 plus 6, 14. Out here, it's gonna be 12 and 2, yes, 14. So my perfect balance will be 3, 2, 2, 3 and 2. The next one, to the base n just tells me the number of, the number of atoms of carbon, hydrogen and oxygen which are present. So ideally, individually, all of them should be to the base n. No need to balance this. We call this formula as sawdust. The last one, FeSO4, Fe is 2, Fe is 1. To make a 2 to start with. Sulfur becomes 2, sulfur is 3. Okay, it's 3 out here. There is 1 also out here. So you have 2 plus 1, 3, 3. Hydrogen becomes 2 and 1, 3. Hydrogen is 2. Now this is an odd number. Let's make it even. You make this even as well. Hydrogen becomes 2 plus 2, 4, 2. Nitrogen becomes 2, 2. Sulfur becomes 2 plus 1, 3, 3. Finally left out is oxygen. 2 fours are 8, 8 plus 4, 12, 12 and 6, 18 oxygen. 12, 13, 14, 15, 16 oxygen. Nope, it's not proper. What you do is, we need more number of oxygen on the other side. Fine. So what we do is, you can increase the number of atoms out here. You double it. Fe2, right? Multiply with 3. 6 Fe. You can make a 6 Fe out here. In this pretext, what happens is sulfur becomes 6 and 1, 7. Now 7 is an odd number. Sulfur out here is 3. 3 3s are 9. So I can make a 3 out here. 3 and 6, 9. Hydrogen becomes 6, 6 and 2, 8. Hydrogen, to make it 8, you should have a 4 out here. Left out is oxygen, guys. Okay. Oxygen is 6 fours are 24, 3 fours are 12, and 2 threes are 6. 42 oxygen. Shit. Out here, 12 threes are 36, plus 4 plus 2. That's balanced for you. So this was a difficult part in balancing. So these are the few reactions with dilute HNO3. Alright, so this was about the reactions. After this, we have a small answer on aqua regia, which usually says that it's not for the syllabus. But I have done aqua regia in HCl part for you all, right? Then we come up with the chemical tests. It is again, chemical tests are nothing but the reactions. And I guess we have done a lot of reactions which are a repetition in the chemical test. So the final part of the chapter to conclude with goes to the brown ring test. So this is the final part of our chapter nitric acid. So if I happen to have a quick review on what we have done till now, first we spoke about the basics of nitric acid on the reactions, right? The reactions, it is called aqua fortis, the Chile saltpeter, the Bengal saltpeter. Then we spoke about the laboratory method. The third part was about, have we spoken about the physical properties? I guess no. We'll talk about the physical properties. The third answer was about the decomposition, the yellow tinge of nitric acid. The fourth answer was about how to remove the yellow tinge, the color of nitric. Perfect. Fifth answer was about the industrial method, which we call it as an Oswald's process. Sixth answer, how to purify it, how to make it 98% pure fuming nitric acid. The next answer was about when it falls on the skin, xanthoprotic acid, the blisters, the painful blisters on the skin. The next answer we spoke about is the indicators, then the reactions, a lot of reactions, and eventually the passivity and few more reactions. All right. If I talk about brown ring test, before the brown ring test, as I said, I'll forget it. We'll talk about the physical properties. Okay, can I say first, nitric acid is an acid, so it is sour in taste. Second, it is colorless. If you talk about the odor of nitric acid, okay, it is a suffocating odor. Talking about, what else can you talk about the nitric acid? It is colorless, it is suffocating odor, it is sour in taste. It is only 50% pure, and that 50% pure is yellow colored nitric acid, yellow tinge, yellowish brown tinge, and 98% pure, that is fuming nitric acid, it is colorless. That's all you can remember about the physical properties. Let's now go with the brown ring test. In the brown ring test, you take a test tube. In that test tube, you take this solution, that is FeSO4, that is iron 2 sulfate. From the side of the test tube, you slowly pour sulfuric acid, and nitric acid should also be taken. So first, in a test tube, actually you take dilute nitric acid, iron 2 sulfate crystals, and pour through the sides of the test tube sulfuric acid. And what you do is you keep it under the running water, a tap, because it's a highly exothermic reaction, and since it being an exothermic, cooling has to be done regularly. What is formed is, FeSO4 reacts with NO, because obviously all the iron 2 sulfate will not be converted into iron 3 sulfate. No, some FeSO4 will react with NO, some FeSO4 reacts with NO to form FeSO4.NO, and this is called nitroso iron sulfate. And this is the compound responsible for a brown ring. So what happens is, after, in a test tube, you add all these three things, you will be left out with something like this. A brown ring will be formed at a junction of two liquids. This is going to be the brown ring. And who is responsible for a brown ring? It is nitroso iron 2 sulfate. At the bottom, you will have sulfuric acid because it is heavier. And above, okay, there will be a solution of iron sulfate or water. Now listen what happens. Even if you slightly disturb this test tube, the brown ring is very unstable. This nitroso iron 2 sulfate is a very unstable compound. It will quickly dissolve and react with H2SO4, and it is going to decompose into H2SO4. So the brown ring will vanish away. It will vanish away once the test tube is even disturbed to a certain extent. So after you actually carry or perform this experiment, you need to be cautious that the test tube does not move, thus the brown ring sustains. Else, because of the heat evolved, the exothermic reaction, the brown ring will decompose when the water and sulfuric acid will mix together. So this is called the brown ring experiment or the brown ring test. And with this, guys, we end our chapter. The chapter named Nitric Acid.